In this illustration, we intend to simulate the stainless steel bolted extended end plate joints under seismic loading in the Abaqus software. As you observe in this picture, the model includes column, beam, end plate, bolt, stiffener, and triangular stiffener. In this question, a cyclic loading is applied to the top part of the beam, and subsequently the hysteresis diagram of the model will be drawn. In this picture, the hysteresis diagram obtained from the Abaqus software have been compared with the experimental results. As you observe, the results obtained from the Abaqus software are similar to the experimental results. In this picture, you can observe the stress contour. In this picture, the results obtained from the Abaqus software have been compared with the experimental results. Actually, we intend to simulate this article in the Abaqus software. The article is entitled Study of Stainless Steel Bolted Extended End Plate Joints Under Seismic Loading. In this picture, you can observe the experimental sample. Also, in this picture, you can observe the hysteresis diagram. I will click on Create Part. I intend to create a geometric shape of end plate. Continue. As explained in the article, the length of end plate is equal to 500 millimeters and its width is equal to 200 millimeters. Done. As you observe in this table, the thickness of end plate for JC4 model is equal to 16 millimeters. So here I'll enter the thickness of end plate equal to 16 millimeters. In the next step, we should distinguish the place of holes on the end plates. To do so, I'll click on Create Cut Extrude. Select this plane, then select this line. Click on Rotate Instance, select Beam, Done, and rotate that 90 degrees about X-axis. In the next step, I will enter the geometric shape of triangular stiffener into the assembly section. Click on Rotate Instance, select Triangular Stiffener and Done, and rotate that 90 degrees about Y-axis. After that, I will move that to a proper place. The interaction between stiffeners and the column has been done by the weld, and we will use tie constraint for the purpose. The interaction between the beam and end plate has been done by the weld, and the interaction among the triangular stiffeners with beam and end plate has been done by the weld, and we will use tie constraint in order to define the weld in the Abaqus software. The other interactions, such as the interaction among bolt and end plate and column, will be defined using the coefficient of friction. I will click on Create Interaction property, select Contact and continue. I will click on Mechanical menu, then select Tangential Behavior. From here, select Penalty. As described in the article, the coefficient of friction is equal to 0.2. Therefore, I will enter the coefficient of friction equal to 0.2. Click on Mechanical menu, select Normal Behavior and OK. This force is actually a tensile force applied to the bolts in order to tighten them on firmly. I will click on Create Load, select Step 1, select Bolt Load and continue. I will select this plane, done, select Brown, select this line. That is indeed the axis of the bolt, and the tensile force is applied towards this direction. As mentioned in the article, the quantity of the bolt load or preload is 170 kilonewton, and this quantity is actually for the bolts with grades of 10, 9. Also, I will enter the quantity of bolt load equal to 170,000 newton and OK. As you observed, a tensile force was applied to the bolts. I will do the same for the other bolts as well. Click on Create Material. Here I intend to define the properties of bolt. I'll click on General menu, then on Density. I'll enter the density equal to 7.8 multiplied by 10 to the power of -9. I will click on Mechanical menu, select Plasticity and Plastic. According to this table, the yield stress of the bolt is equal to 995 megapascal, and the ultimate stress is equal to 1360 megapascal. I will click on Mechanical menu, select Elasticity and Elastic. Young modulus is equal to 210,000 megapascal, and Poisson ratio is equal to 0.3. Here you observe the deformation obtained from the Abaqus software is very similar to the experimental results. As it can be observed here, the deformation obtained has a close similarity to experimental results. In the next step, we intend to draw the hysteresis diagram of the model. Actually, we intend to draw this diagram in the Abaqus software. The horizontal axis is displacement and the vertical axis is force. I will click on Create XY Data, select ODB History Output and continue. Here I will select all reaction forces. Click on Save As, select Sum, and OK. Here I will select Displacement and click on Save As. In the next step, I'll click on Create XY Data, select Operate on XY Data, and continue. Here I'll select Combine. First, I'll select U3, then Total Force, and click on Save As. Here you observe the hysteresis diagram obtained from the Abaqus software. I'll transfer this diagram to the Excel software. The first column is displacement, the unit of which is millimeter. The second column is force, the unit of which is Newton. Here the diagram having been drawn with blue color is the one obtained from the Abaqus software. As you observe, the results obtained from the Abaqus software are very close to those mentioned in the article, indicating that this question has been simulated properly in the Abaqus software.